This is a lecture by Farouk Kalemi, narrated by Angad Buttar. This is part 2 of the two-part series of lectures on hazard functions for a combination of causes. If we can assume that various causes are independent of each other, then the hazard function from all sources can be calculated as the sum of hazard function from each source. This is a very helpful concept as it allows us to calculate the total impact of multiple causes. For example, under assumption of independence, the hazard function for a smoker exposed to asbestos is said to be the sum of hazard due to smoking plus the hazard due to asbestos. This attributable risk due to cause is calculated as the ratio of its source specific hazard rate divided by the hazard function from all sources. An example can help demonstrate this concept. If the hazard function for medication error caused by a fatigued nurse is 1 in 1,000, and the hazard function for medication error caused by illegible prescription order is 2 in 1,000, what is the attributable risk to the fatigued nurse? Using the formula for attributable risk, we calculate this as the ratio of a nurse's hazard rate over the total hazard rate. In this case, it is 33%. In contrast, 66% of the medication error risk is attributable to the physician's poor prescription writing skills. The most probable cause of the event is the physician's ineligible writing. In this fashion, relative attribution can be made to separate risks. Correct attribution, of course, is important to priorities one sets for remedies to the problem. If 66% of risk is due to ineligible prescriptions, then it might be best to resolve this problem first before addressing the problem of fatigued nurses. Of course, the best action of all is to address both causes, but if we cannot and need to set a priority, the analysis shows how to focus on key causes that are more responsible for the observed sentinel events. It is often not possible to collect sufficient data to estimate the possible combination of impact of multiple causes of the sentinel event, and each cause may be present or absent. Then there are 2 to the power of 5 possible combination of causes, some of which are quite rare and therefore unlikely to occur even in long streams of data. In these circumstances, the effect of missing combination of causes can be estimated from the available hazard functions. The first step is to set all hazard functions for combination of causes and a binding constraint to 0, as in these circumstances, the constraint will nullify the effect of various causes. By the word binding constraint, we mean that when the constraint is present, the probability of the sentinel event is 0. For example, a cause of medication error is the miscalculation of the necessary dose. A constraint for this cause is verification by an independent observer. If a nurse miscalculates the dose, but the error is found in verification, then there will not be any medication errors due to miscalculation. Of course, one might argue that in very rare situations, the verification may be an error too, in which case verification is no longer a binding constraint. It reduces the hazard of miscalculation, but not to 0. In the second step of completing missing hazard functions from available estimates, the hazard functions for causes that only have an effect when they simultaneously occur together are estimated. Usually, the conditional probability of the sentinel event from the combined causes can be estimated from a registry of sentinel events. This is shown as P in the above formula. The individual cause hazard functions are not available and can be estimated to be 0 or minimal because the causes will have no effect or a minimal effect unless all of them are present. For example, for a patient to fall, there must be a slippery floor and some cognitive impairment. Both are causes of falls, but neither is likely to have an effect by itself. In these circumstances, The hazard of a slippery floor or cognitive impairment by themselves is minimal, but the combination of these two causes makes falls much more likely. In step 3, missing hazard for combination of non-interacting independent causes is estimated as a sum of the available hazard functions for each of the causes. For example, wrong side surgery might be due to erroneous marking, not following the nurse's marking, or wrong information from the patient. The combination of these three causes might be considered non-interacting and independent. Under this assumption, the missing hazard function of the combinations is the sum of the hazard associated with each cause. In the fourth step, we estimate that the missing hazard of the combination of the interacting dependent causes. To do this, one of the course needs an estimate of the interaction between the causes. When two causes interact, their joint hazard is different from the sum of the two. In calculating the combined effect of a set of causes, it is important to use pairwise joint hazard rate instead of the sum of the hazards of each cause. If the interaction increases the hazard, then the maximum of various sum of pairwise combination of the hazards is selected. If the interaction decreases the hazard, then the minimum of various sum of pairwise combination of hazards is calculated. For example, assume that three causes X, Y, and Z interact to increase the risk. The combined hazard of these three risks is calculated as a maximum of sum of pairwise combinations of causes. For example, if poor training and fatigue interact with each other to increase medication error rates, then the combined hazard should be used in estimating the combination of these two causes and other causes. So, if we want to estimate the effect of poor training, fatigue, and similar bottles, then the combination hazard is equal to the hazard of poor training and fatigue plus the hazard associated with similar bottles. It is also possible, though rare, that we have the estimate for the combined effect of several non-interacting independent causes. In the absence of any other information about the relative impact of each cause, the hazard associated with each cause could be estimated to be equal. The take-home lesson for this first lecture is that hazard functions are key to understanding relative contribution of multiple causes to sentinel events. Please use the course website to ask questions and rate this lecture.